Okay, so my name is Harald Thommesen, and I will now give an update on the spider analysis. So I'm a postdoc here in Oslo. And yes, so you've seen this slide several times. So Ingun showed it this morning, and that's basically the big picture of Cosmoglobe. So just to sum up, that we want to add many different data sets and perform this end-to-end analysis with Commander 3. And last year at the kickoff meeting in June, I showed the first results of Spider when we want to add this to the analysis. And at that point last year, we were only working with the Spider channel, with the Spider data, without any other data sets. And we were only looking at one of the two channels that Spider has. And yeah, now on the next slides, I will show you what progress we've made ever since. And yeah, but first I will recap on how we do analyze the Spider data. So we start out with the raw data of the instrument, which is about 1.6 terabytes of data. And then we segment this data into 10-minute chunks, where each chunk contains 10 minutes of all the available time streams that we have, like the TOD, the pointing or the polarization angles and the flags and so on. And then we downsample these data by a factor of 5. So we reduce the sampling frequency from 120 hertz down to 24 hertz to basically reduce data volume, and it will only cost us basically high frequency noise. And then we further compress these data with a technique called Huffman compression. And yeah, we compress the data streams that we can compress with this technique. In our case, that's the pointing information and the flags. And finally, we create standardized data files that Commander can read. So with the same structure that all the other data sets have. And then we end up with about 2,000 files, which make up about 180 gigabytes on disk for the two Spider channels. And then we read these data into Commander. And yeah, most of the code already exists inside of Commander in order to produce frequency maps. But yeah, we need to deal with any characteristics that the data set has that hasn't been taken account yet by the implementation for other data sets. And for the Spider data, the big characteristic are huge jumps in the time streams. So this is a raw TOD sample, which shows exactly 10 minutes. And you can see that we have huge spikes, which are iridium pings, which happen when the instrument communicates with the ground. We have cosmic ray spikes, but yeah, the big problem are those huge jumps in the offset level. And these we need to take care of. And yeah, the first step that we do is that we flag out the iridium pings and the cosmic rays, and then we fill the gaps with a constrained realization. And yeah, and then we compute a standard deviation, a moving standard deviation along the time stream, which then will show nice peaks wherever where a jump occurs. So these spikes in the standard deviation basically trace the jumps in the time stream. So we define a threshold, and wherever the standard deviation exceeds this threshold, these positions we mark as jump positions. And then we can average all these offsets, subtract them from the data, and yeah, then we want to achieve a residual which looks white. So the first step we have to do is that we need to deal with the correlated noise. And the correlated noise model that we use is a simple 1/f noise model, where we fit 3 parameters, the noise floor, the knee frequency, and the slope to the Fourier spectrum of the residual. And then we use these fitted model parameters to compute the correlated noise in time domain. And we do that by solving the Wiener filter equation. And in order to get a random sample, we add random fluctuation terms and solve for that. And that gives us the correlated noise in time domain. And when we subtract that off of the residual, and if we have gotten good solutions for the noise term and the offsets, then we will get a residual which looks white. And we do that for all the 2D segments that we have. And so to sum up, we start out with the raw data, which has huge jumps. We solve for correlated noise and for the jump offsets. We subtract these off of the data. And this gives us calibrated data, which we then feed into a binned map maker. And that's basically the result, the main result that I showed last year at the kickoff meeting, which was the frequency map for the 150 gigahertz channel. So what has happened ever since? So we repeated the analysis on the second channel, namely on the 90 gigahertz channel. And then we performed a map domain analysis and produced the first joint CMB map, which includes the data of Spider, but also of WMAC and Planck LFI. And then we did our first time domain analysis. So which the first, in the point that we compute the frequency map for Spider from scratch instead of pre-computing it like in the first case. Okay, so let's look at the map domain analysis. For the map domain analysis, we use the two frequency maps that we pre-computed, and then we add Planck LFI and WMAP to Commander. And that's all happening in map domain for now. And it's the same setup as was used for Beyond Planck. So we add Planck LFI, we add Planck 857 gigahertz to constrain thermal dust intensity. We add Planck 353 gigahertz to constrain polarization. We add WMAP to constrain low frequency foregrounds. And then we add Haslam at 400 megahertz to constrain synchrotron. Okay, so these are the frequency maps of Spider that we feed into Commander for 90 gigahertz, 150 gigahertz. And this is the joint Commander CMB map that we get out of it. And that's the first time that we actually join full sky and partial sky data. Like Spider is partial sky, and Planck are full sky. And here we can see the Spider field, which is a lot less noisy than outside, where it is dominated by Planck data. Inside the field, it's dominated by the Spider data. Okay, so let's now move on to the more interesting case, because actually we want to do end-to-end analysis. So we performed the time domain analysis where we actually produced the Spider channels from scratch. So in the earlier case, we pre-produced them and fed them into Commander. Now this setup resembles a lot more the final goal that we have in mind, where we want to have all the frequency channels produced from raw data. But we start out with only performing TOD analysis on the Spider data and still keeping the Planck and the WMAP data in map domain. First of all, it's a lot easier to debug. And secondly, that way we can perform it on one single node. Okay, so one comment on large scale cut. So in this analysis, we perform a large scale cut where we project out the low scales in the Spider field. So in our case, we chose a cutoff of L equal to 50. So all the modes lower than 50 don't contribute in a map of Spider. And to do that, we apply a projection operator on the raw map, which projects out these modes. And yeah, in order to project out modes, we need base functions. And yeah, typically you would use historical harmonic basis functions, but when you apply a mask, these are not orthogonal anymore, so you can't use them as base functions anymore. So you need to create a new orthogonal basis with a certain cutoff and on the mask. And this is done by applying eigenvalue decomposition. And this new basis is stored in this P naught operator. So when you apply this operator on the raw map, this gives you the large scales of the map. And by subtracting these off of the raw map, you are left with all the scales higher than 50. Okay, and we applied this on the spider data, which is very useful for partial sky data. Okay, so when we look at the output of Commander, we are getting an ensemble of CMB maps. So now we are looking at different CMB samples. So these are just different iterations. And here you can see the spider field. And since we projected out the large scales of spider, the inside of this map, the large scales are dominated by Planck noise, while the small scales are dominated by spider data. Okay, and from these samples, you can compute the posterior mean map, which is just the mean of all the CMB samples that we got. Furthermore, you can compute the posterior standard deviation map, where you can see the spider field, but also you can see the Planck scanning strategy. So as you run Commander, you have access to all the components. So we also have access to all the components during pre-processing of the data. So here we're looking at how the subtracted jumps that we subtracted off of the raw time streams, how these look like in map domain for 90 gigahertz and for 150 gigahertz. And we can look at the correlated noise in map domain for 90 and 150 gigahertz. Okay, and then we can look at all the foreground components. So this is dust temperature, dust polarization, synchrotron, synchron polarization, free emission, spinning dust. And then we can zoom in onto the spider field. And yeah, this is dust in the spider field, synchrotron in the spider field. And then we have spinning dust and free emission in the spider field. Here we can see that, it's not perfect yet because we see this imprint in the spider field, which looks like CMB. So that tells us that we still have some calibration, that calibration isn't right yet, or that we have a problem with the beam. And finally, we looked at the temperature power spectrum inside the spider field, which agrees well with the Lambda CDM model. And so what's to do in the future is to figure out what this issue is coming from in the AME and free maps. We need to work on polarization because earlier I just showed the temperature power spectrum. We still have an issue with polarization, so that's why I haven't showed it yet. And the final goal is that we want to turn on TOD analysis for all the channels and not just spider. So that's also on our to-do list. Okay, and yeah, thank you for the funding and thank you for your attention.